Now, the title of my talk is Emerging Technologies in Renewable Energy Sources, the recent advancement in solar distillation. Different solar water desalination processes exist, such as active and passive basin type solar stills, and systems also working on humidification dehumidification principle have been used to produce fresh water from saline water. Among these processes, solar water desalination systems based on humidification dehumidification techniques is one of the simple and most efficient techniques, and performance of these systems have been studied and improved by several researchers recently. The humidification dehumidification process is an interesting technique adopted for water desalination when the demand is decentralized. As can be seen in figure, the proposed solar water desalination system with the humidification dehumidification technique consists of a double pass flat plate solar air heater, which heats up the air before it get inside the humidification chamber. It is with two glass cover, humidifying tower, and the storage tank and dehumidifier exchangers are also the components of the unit. A schematic view of the system that is based on the idea of the closed water and open air cycle is presented in the figure. In proposed system, air is heated by using double pass flat plate solar air heater, whereas water is not heated, unlike it was in case of solar stills. By heating the air, V increases the water carrying capacity of the air. In other words, we increase the vaporization of the water. Firstly, the process air at the ambient condition is forced to flow through the upper channel of the double pass flat plate solar air heater, where it is preheated. The preheated air is further heated by passing it through the lower channel of the solar air heater. Secondly, the heated air leaving the double pass flat plate solar air heater enters into the humidifier and is humidified by saline water that is coming from the water storage tank in the form of spray droplets. Eventually, the air carrying water vapor is passed through the dehumidifying coil surface, where water vapor condenses and turns into fresh water. Also, saline water leaving the humidifier is collected back in the storage tank and recirculated to the humidifier once again. The energy balance equation for the air heater are shown. Where first air pass, absorber plate energy balance equations are shown. Humidifier, dehumidifier energy balance equations. The radiation heat transfer coefficient between the two glass cover can be found by the relation shown. The convective heat transfer coefficient for the air flowing over the upper glass cover can be given by the following empirical relation shown by equation number 14, then 15, then 16. And the radiation heat transfer coefficient from the second glass cover to the sky can be given by equation number 17. And then 18, the natural convection heat transfer coefficient between the first and the second glass cover is given by the equation number 19. The following correlation proposed by the Holland can be used to calculate the Nusselt number, and by the equation number 20, the positive exponent means that the value of this term is equal to 0. If the term is negative, then Ra is shown, which is nothing but the Reynolds number, by equation number 21. Thermal properties of the moist air suggested by the researchers as the function of air temperature are evaluated by the equation 22, 23, 24 and 25. The forced convective heat transfer coefficient inside the upper channel of the double pass flat plate solar air heater can be found by the relation shown in equation number 26, where equation number 27 gives us the hydraulic diameter. For laminar flow, the Nusselt number may be calculated from the equation number 28. For turbulent flow, the following correlation can be used to determine the Nusselt number, equation number 29, where Reynolds number is and F is the friction factor, and they are given as follows: equation number 30 and equation number 31, whereas the radiative heat transfer coefficient is given by the equation number 32. The radiation heat transfer coefficient between the copper absorber plate and the first glass cover is calculated by equation number 12, replacing by Tg2 with Tp and epsilon G with epsilon P. We can find out the various heat transfer coefficients as shown in equation number 33 and 34. Applying the assumption 4, we can find out the temperature by equation number 35 and heat transfer by equation number 36. The convection heat transfer coefficient Hc from P to A can be found inside the lower channel of the double pass flat plate solar air heater, are evaluated from the equations shown above, which are used to calculate the convective heat transfer coefficient for the upper channel and thermal properties of the air flowing inside the lower channel of that should be taken at the mean temperature of the second air pass, and the heat transfer can be obtained by the equation number 37. Applying the assumptions 8 and 9, the following qualities can be obtained. For example, the temperature and mass of evaporation by equation number 44 and 45, and the heat transfer by equation number 46. The above mentioned assumed initial temperature are used to determine the heat transfer coefficient that depends on the temperatures. Afterward, by using the assumed initial temperatures and calculated heat transfer coefficients, the system of the first order ordinary differential equations above are solved numerically to obtain new temperature that will become initial conditions, and the process above will be repeated to solve the equation for the next time step. As a result, after working the inlet water and air temperature to the humidifier at each of the time intervals, the temperature of the air leaving the humidifier can be calculated from equation number 8, and temperature of the air leaving the dehumidifier can be evaluated from equation number 9. In the dehumidifier, the quantity of the condensate water each of the time interval is calculated from equation number 43 by knowing the inlet and outlet air temperatures. The productivity of proposed desalination system depends upon the humidifier and dehumidifier outlet temperatures. The effect of various operating and design variables on outlet temperatures of humidifier and dehumidifier have been discussed below. As can be seen, the productivity of the proposed system increases up to 10% by using a double pass flat plate solar air heater as compared to the single pass flat plate solar air heater. In absence of any air heater, the productivity decreases by 80% and 70% if compared to double pass air heater and single pass air heater respectively under the same operating conditions. The above result shows the superiority of double pass solar air heater over single pass solar air heater, particularly for proposed desalination system. As can be seen in the graph, the productivity of the system increases by increasing the air mass flow rate to an optimum value and decreases after that value. This mass flow rate of air, which is 0.03 kg per hour, productivity 5.5 kg per hour, is optimum value after any increase in it does not contribute for productivity. It is clear that up to optimum mass flow rate of 0.03 kg per hour system gives a 400% increase in productivity with 200% increase in air mass flow rate. After that, even with 70% increase in mass flow rate over the optimum value, 40% decreased productivity can be observed. As can be seen, the productivity of the proposed system increases up to 10% by using a double pass flat plate solar air heater as compared to the single pass flat plate solar air heater. Drop in productivity 80% if compared with double pass. There is drop in productivity by 70% if compared with the single pass in absence of proposed system. Now, the superiority of double pass solar air heater over single pass solar air heater, particularly for proposed desalination system, can be observed. The proposed process has several attractive features which include operation at low temperature. Number 2, ability to utilize sustainable energy sources, that is solar and geothermal. Number 3, and requirements of the low technology level. Output of solar still mainly depends on the temperature difference between the basin water and glass cover. The more temperature difference increases the rate of water evaporation from the basin of solar still, thus results in increasing the condensation of water, thus increases in the distillate output. Vice versa, the lower temperature difference lowers the output of the solar still. This temperature difference can be increased by either number 1, increasing the temperature of water in the basin, active or passive ways. Number 2, decreasing the temperature of glass cover by flowing a cooled water over it. Number 3, combination of both stated points above, that is increasing the basin water temperature and decreasing the cover temperature together. There is one case when the multiple effect diffusion still can be used. As you can see, the vertical walls of metal, on outside there is wicks which are mounted and inside there is a cooler surface. In this case, the distillate output is generated through a condensation occurring both beneath the double glazed glass cover and also on the inner surface of the vertical metallic wall, on the other side of which there are wicks on which the waters are flowing to keep it cool. On the opposite side of this wall, wicks transport saline water. As the saline water contacts the metallic surface, it cools and subsequently evaporates due to heating. Simultaneously, on the opposite side, cooling induces condensation. The latent heat of condensation is released to the vertical wall later on, which is taken away by the water dribbling over the wicks. The vertical walls get heated. Heat is transferred to the saline water trickling over it and further evaporation takes place. At the same time, condensation happens on other side of metallic wall, and this process goes on. These are called multiple effect solar stills. There can be tubular type solar stills as well. The figure shows a tubular solar still consists mainly of transparent cylindrical tube in which the rectangular absorber is placed. Due to gravity effect, the condensed water flow down over the inner surface of transparent tubular cover and is stored in the collector provided at the bottom point of trough due to gravity effect. Another one is the chimney type solar still. As can be seen in the figure, the saline water enters into chimney through the heat exchanger and then enters into a still. It is evaporated in the still due to the solar radiation received as latent heat of vaporization. The vapor diffuses into the chimney and condenses on the external fins of the heat exchanger. The distillate water is collected at the base of the chimney and can be drained out for some useful purpose. Another one is a stepped solar still. As you can see in the figure, the inclined wick solar still is modified here into the stepped basin solar still. The modification helps to create uniform wet wick film, thus helps to enhance the production rate of inclined wick solar still. It is a combination of a number of inclined wick solar stills as much as we want. Another one is solar still with separate condenser, in which the separate condenser other than the conventional glass cover through which radiation is received helps to increase the temperature differential between the basin water and condenser cover finally, which leads to increase the rate of condensation, which enhances the amount of distillate output produced per unit area. Normally, the separate condenser is being kept under shadow. There is no sunlight falls on separate condenser, and normally it is used of metallic one, so that we can have two different condensing areas. One is the conventional, which is the glass one, the glass cover inner one, and another one is a separate condenser which is of metallic, of metal, made of metal. It can be seen the separate condenser can be metallic or glass that can be arranged to keep in shadow for remain cooler for creating the temperature difference between water and condensing cover. Another one can be solar still coupled with solar concentrator, in which the parabolic concentrator heats up the water, and the water can be used for two purposes, for heat water purpose and for sending the heated water to the basin. In this arrangement, the basin water is being supplied from solar concentrator at very high temperature that get evaporated very soon and also get condensed on inner surface of glass water because of the temperature difference between water and condensing cover, because in this case the water temperatures is very high. The maximum output is produced has been noticed approximately 10.77 liters per meter square even. The solar is still coupled with air cooler. Air cooler means the cooled air from an air cooler is sent or blown over the condensing cover. Solar is still coupled with air cooler to harness the cooling effect of the water in the cooler tank. Normally, we can either blow the air cooler on the surface of the condensing cover and otherwise we can also flow the water of the cooler tank, which is at corresponding wet bulb temperature, to the dry bulb temperature. Somvanshi and Tiwari proposed integrating solar still with an air cooler, and this way when we are flowing cooler water over the glass cover, we are reducing the temperature of the glass cover, thus we are increasing the difference between water temperature and condensing cover temperature. In this design, evaporatively cooled water flows over the solar still's cover. This approach serves to create the temperature between the water and the cover, leading to a reported increase of approximately of the order of 58% in the annual distillate output in the climate of Jodhpur, India. Solar still coupled with solar pond. The solar pond is heating the water, and that water is used in solar basin. Then solar still coupled with PVT system. As you can see in the figure, there is a flat plate water collector which is heating the water. Later on, that water is going to the solar still, which is kept over the flat plate collector, and that water is going to the solar still by using a pump. That pump is run by the photovoltaic cell, which are mounted on the bottom side of the flat plate collector. So it is here 3 in 1, solar still coupled with photovoltaic thermal system, and here we are not using any conventional source of energy for sending the hot water from the flat plate collector to the solar still. It is found that exergy based energy payback time is lower, of the order of 89.90% and 44.45%. Energy production factor is higher by 46.67%. Using black dye with water in the basin. This black dye is, if kept inside the water of the basin, it collects more heat. At the same time, it provides more surface for water to get evaporated. To increase the water temperature in the basin, a researcher Soda et al. Suggest to use black dye in the basin. By doing this, they found that the productivity increases of the order of 48% by using black dye for 14 centimeter water depth, as can be seen by the graph as well. Using of reflectors with black dye in the basin, a researcher Tamineni suggested to use black dye and reflectors. A schematic diagram is shown in figure. They found that the efficiency increases about 30 to 35% by using black dye and reflector mirror together. Using fins in the basin of solar still. There are, in the figure, there are different type of fins or different type of corrugated surface have been shown that is being kept within the basin for increasing the temperature of the water. All these arrangements finally increases the temperature of water, and it also increases the evaporation of water. Higher the rate of evaporation, the higher will be rate of condensation as well, if we can ensure the temperature difference between water and condensing cover a bigger value. Another scientist, O'Meara et al., experimentally compared the performance of conventional solar still, finned solar still, and corrugated solar still, and they found with finned and corrugated solar still the productivity increases approximately by 40% and 21% respectively. In this case, the daily efficiency for finned, corrugated and conventional solar stills were approximately 47.5% and 41% and 35% respectively. Using strip lining attached to the absorber plate, a researcher Ayuthia et al. Suggested to use strip fins on absorber plate. They found that the productivity of the modified solar still was increased by 15.5% compared to that of a conventional still. Using porous fins in the basin of the water for the same reason, for increasing the evaporation rate, for increasing the water temperature, as suggested by Srivastava, a researcher et al., the basin water primarily acts as a thermal storage which supplements the evaporation process during low insolation, besides giving a reasonable nocturnal output even after the sun set, 56% higher per day. Time distillate and 48% higher for 24-hour duration was obtained in the month of February over conventional still, whereas in the month of May 23% higher daytime and 15% higher for 24-hour was achieved. Using finned absorber plate solar still, as can be seen in the figure, the shape of the fins, as suggested by a researcher Al-Sabai et al., it was found that the productivity of the finned plate solar still increases with increasing the fin height. However, it decreases with increasing the fin thickness and fin number as well. A daily productivity of the order of 5.377 kg per meter square per day was obtained when the height and thickness of fins were 0.04 meter and 0.001 meter respectively. Using pin fin of wick element, a researcher Alain et al. Suggested to use pin fin of wick elements placed on the absorber plate of solar still. They found that the system efficiency of about 55% is recorded when pin fin wick is used. An enhancement in the still productivity of more than 23% is recorded during this set of experiments. Flowing water over glass cover of a solar still, cooling glass cover, it means cooling glass cover, is shown in the figure. 7 to 10% increase in annual efficiency of a single slope solar still as per Lawrence has been found. There is 10% increase in annual efficiency of the multiple wick solar still, and Abu Hilja got about 20% increase in daily distillate output of solar still. Then using the nanofluid with cover for cooling, researcher Srashir et al. Suggested to use the water over the glass cover as a feed water. The output yield is improved by about 47.8% and 57.6% using copper oxide and graphite particles respectively, while the daily efficiency of the conventional still is 30%. Now, small solar distillation plant cooled by water flow over the glass cover using the garden fountain water. As can be seen in the figure, there are a number of solar stills which are connected with the fountain, and the fountain water is flown over each and every glass cover Tiwari and Somvanshi, a researcher, proposed a small solar distillation plant cooled by water from garden fountain. They found the daily distillate output enhanced of the order of 61% and the increase in annual efficiency of the single slope and multi-wick solar still about 15.5% and 17.4% respectively. As can be seen, some other methods of enhancing output of solar still, Tiwari and et al. Implemented an internal glass wiper. The maximum total yield improvement 22.1% was obtained for the WISS for a total yield value of about 2.575 liter per day for a pair of consecutive day, while the maximum total yield improvement across all the days against the CSS system is found to be 33.7% for a total yield value of 2.567 liter. Thank you.